Okay, you'll see why I use the word next generation in a moment. So DarkSage is a model that I've been developing for a number of years. I actually started developing it in the last year of my PhD back in 2015. And I released the first version of this in 2016, second version in 2018, and what I'm about to present today is the key parts of the updates that I've made since then. So sort of version 3 will be coming out within the space of the next month. This is, as you can imagine, 5 years in the making. There's absolutely no way I'm going to touch on even a fraction, really, of what's gone into this model, but hopefully I'll at least give you some nice highlights. Okay, so for those who are unfamiliar, so the younger people or a refresher for the older people in the room, how does a semi-analytic model of galaxy formation work? You first need to run a cosmological n-body simulation. There's one example here. Within that simulation, you identify all of your bound structures, which we commonly refer to as halos, and all of the sub-halos as well. Track those back through time, build up what's called a merger tree, such that you have the history of every halo that has interacted with any other halo. So a tree within a kind of a forest is the history of a given halo and everything else it's interacted with. And this is what feeds as the input into a semi-analytic model. So these are, gravity-only simulations. We often refer to them as dark matter only. They are dark matter physics only, it's not like the baryons aren't there. Their mass is present, of course, just not the physics that describes them. The physics that describes them comes in the next step, which is the semi-analytic model. So the way that this normally works is that you populate every halo with baryons, and you have a series of coupled differential equations that tell you how baryons should move, both their mass and angular momentum and other properties, between a series of different reservoirs. So this picture that I've actually pulled out of my PhD thesis shows you what a classical semi-analytic model looks like, where it's got one reservoir to describe your hot gas, one to describe your cold gas disk, one to describe the stellar mass, one to describe a supermassive black hole, one to describe gas that's possibly been ejected out of the halo, and then some various arrows describing physical processes that tell you about when and why you should move mass between different reservoirs. DarkSage is different and always has been in that it doesn't treat each of these as a single reservoir. It breaks them down into a series of different components. And what this does is it gives you extra dimensionality, predictability that most semi-analytic models can't do. So typically a semi-analytic model is very good for statistical studies of integrated properties of galaxies. What my model does is allow you to do things with structural detail. Okay, so one of the things that's new is that this has now been coupled to the Millennium TNG simulations. Why not Genesis? It's a practical answer. Didn't get done in time. Data didn't interface as well. Wasn't quite the right resolution. Millennium TNG didn't have any of those problems, and also there are hydrodynamic runs with these, which are going to allow for object-to-object comparison, which is very helpful for comparing against galaxy formation models that are built in a completely different way. Okay, so this is I won't tell you more of the specifications, I don't have time. Right, okay, so so I mentioned DarkSage breaks things down into more detail. So there are 35 distinct gas components in a DarkSage galaxy / subhalo. Okay, so there are 30 that describe the ISM. These are just annuli. They are fixed in terms of specific angular momentum. 30 is a little bit overkill, but I'd rather be overkill than underkill. There are 3 what I call intrahalo components. So this is the CGM, if you like, or the intracluster medium, depending on which mass scale you're looking at. One of which describes the static hot halo, for which there is gas available to cool onto the galaxy. 2 that describe gas that has come out of the galaxy that has been affected by feedback. 1, which I call the fountaining reservoir, so it's not got enough energy to escape the halo, and then one that's called the outflowing reservoir, which will end up escaping the halo. So actually, was it Bron's talk yesterday I found quite interesting because they've observationally broken them down into very similar things, so there's possibly a point of comparison for us there. And then 2 extra halo components, as I call them. So one is the ejected reservoir mass that has come out from the galaxy as a result of sheetic outflows, and then stuff just being stripped from satellites outside of the virial radius. The stellar components are similar, except they add an extra dimension. So for every single annulus in the stellar disk, there are 30 bins of age. Okay, so what this means is that we can now do feedback non-instantaneously. There's a whole there's a stellar evolution population model going on inside of there, which tells me when supernovas should be going off based on when stars are formed. All of that's tracked. So you can build up a 2-dimensional picture of age and radius or angular momentum. They're 1-to-1 in the way that the model is constructed. Two bulge components, one that's built through gravitational instabilities within the disk, so that's secular, and one that is built up through mergers. There is intra-halo stars. We've just heard about what intra-cluster light is. This is that. Okay, that's built up through the disruption and stripping of satellites, and then one extra halo stars, as I like to call it. So this is just stuff that's been stripped and is outside of the virial radius. Okay, so I mentioned there are two outflow channels which are very important, one of which one of which has the energy to go all the way out and one of which doesn't. I guess I got ahead of myself there and I can just skip that slide. Great. Okay, one of the things that makes dark stage unique as well, it's not just the extra dimensionality. What I've done is I've managed to reduce the number of free parameters down to 3. Now, for context, most semi-analytic models have between 10 and 20 free parameters. And the way that I've managed to reduce this down to 3 is by basically redoing a lot of the physical prescriptions that are in there from scratch. Now, I've had conversations with Lars about how there's no such thing as a galaxy formation model that's derived from first principles, really, but I've tried to get as close to that as possible. And it turns out that there's a whole bunch of redundancy, and it doesn't just turn out, it's obvious when you take the time to do it, and I think everyone else who works on galaxy formation knows this, that everything's coupled, right? And so you can treat every physical process that's important to galaxies phenomenologically and separately, and then have its own set of parameters to define that, and then try to calibrate them all. Or you can spend 5 years figuring out how they're mathematically coupled and then write a 26-page draft that has literally 110 equations in it. That's no joke. That's the current state of my paper. And once you do that, you can actually find there are just 3 key numbers that you need to calibrate. So the ones that I have here, the first one is how you deal with gravitational instabilities. When one's picked up, so 2 q less than 1, the model goes, okay, I've got too much mass. That mass needs to go somewhere else. It can go through the disk, or it needs to be kicked out of the galaxy. There's one parameter that controls that ratio because I cannot come up with a physical way to derive that from first principles. So I've had to just put my ignorance in there. The other one captures a lot of ignorance in terms of how stars form and evolve. It boils down to essentially the average energy per supernova that is coupled to the ISM and the CGM, but it actually has a lot of other factors gone into it, not just that. And then there is the radiative efficiency of material that accretes onto a black hole. Okay, which if you have a model for black hole spin and you assume that everything goes onto an accretion disk and gets down to the innermost stable circular orbit before it's captured, you can derive what this should be, but predicting what the distribution of black hole spins should be is a whole other kettle of fish. And so for that reason, I decided to leave this as a free parameter. Okay, so then I had to calibrate the model. I had to decide what I was going to calibrate these things on. I decided to pick the 3 classic things, which are the stellar mass function at redshift 0, the H1 mass function at redshift 0, and the cosmic star formation density history of the universe. Okay, so you can see in the top 3 of these panels, those are those 3 observational things. The sort of reddish points are the real data. And this is calibrated using a particle swarm optimization technique. What you're seeing here, the points of the parameter space that are sampled as the first run. So it's a random selection of points in there. And then we go through the runs where the particles talk to one another and say, oh, I'm finding a better chi-squared over here. Oh, I'm finding a better chi-squared over here. Why don't we come hang out? And eventually we'll find the area of parameter space that gives us the best joint chi-squared across all 3 things. And then we could look back across all of the runs and see how well that model performs. Now, it's not a perfect match to any one of those observations specifically, bearing in mind that it's trying to fit all 3 things at once. If I try to just fit one instead of the other 2 at the same time, there is no doubt that it would be able to do one with a lot better detail. But often we get too caught up in calibration anyway. Thanks, yeah, I've got, yeah. Cool, okay, so what can dark stage predict that other semi-analytic models can't? Mass loading factors is 1. The entire way that feedback is done is all just energy conservation, right? It's literally just equations derived from energy conservation. There's no explicit input about how mass should load. It's predicted in the model. And so you can compare in the right-hand panel to what is assumed in some other semi-analytic models as an example, and it does kind of fall within the range there, which is kind of nice to see that other people aren't assuming things that are crazy. And you can try to compare to observations as a function of stellar mass, which I put some points on here, and you might go, oh, wow, look, Adam, your model's crap. But actually, to be honest, these data are definitely not measuring the same thing as what I'm showing, and they've definitely got huge systematic errors. So I'm not worried about that in the slightest. Yeah, I'm not taking the piss. Like it's a very difficult comparison to make. Right. The other thing you can do is, because I've got all those age bins, I realize I'm about to go into question time. You can start showing the entire history of galaxies by parts, if you want. And this is all just from one snapshot's output now. All of that information is there. So you can look at the buildup of mass in stellar disks, or in their bulges, or in their intra or extra halo stars. You can look at the metallicity history. All of that information is there at your fingertips from a single output. And you can even do this on an annulus by annulus basis within galaxies, which is what those dashed lines kind of represent. So I don't really have time to like let that sit up and for you to digest it. I will just leave you with a few slides telling you what the salient new features of this are, and to say that if there is something that you want to see in this, like if there's a particular prediction you want me to show in this paper, come and talk to me very quickly, because this paper has to be out in 4.5 weeks, because that's when my job ends, and I will not be doing any work on it after that point. So get in quick. Okay, thank you.